In today's video, we are going to explore the concept of free body diagrams and learn how we can effectively use them to determine the resultant force acting on an object. When we talk about free body diagrams, we are simply referring to basic illustrative sketches that represent all of the forces currently being applied to a single object. These forces are displayed visually using arrows, known as force arrows. Each arrow signifies a specific force and shows the direction in which that force is acting. Let us take the example of an airplane in flight. If we wanted to draw a free body diagram for this aircraft, we would begin by sketching a simplified representation of the plane and then add arrows to represent all the forces acting on it. There would be one arrow pointing forward, which would represent the thrust generated by the plane's engines. Another arrow would point backward to show the air resistance or drag that opposes the motion. Then we would include a downward-pointing arrow to represent the weight of the plane, which results from gravity. Finally, we would draw an upward-pointing arrow to represent the lift force that is generated by the wings as the plane moves through the air. Because forces are vector quantities, each of these arrows must include both a magnitude, which refers to the size of the force, and a direction, which shows which way the force is acting. The direction is shown by the orientation of the arrow, and the magnitude is reflected by the length of the arrow. To be more specific and scientifically accurate, we also label each arrow with values in newtons, which is the unit used to measure force. Since these forces act in different directions, some of them will work against each other and effectively cancel each other out. Once we have accounted for all of the forces acting in opposite directions, what we are left with is called the resultant force. This resultant force can be thought of as the net or overall force acting on the object at that moment. The easiest and most systematic way to determine the resultant force is by examining the horizontal and vertical components separately. This means we calculate how much force is acting in the up and down directions, and then how much force is acting in the left and right directions. Let us look at the vertical forces first in our airplane example. Suppose the force of lift going upwards is 80,000 newtons, and the weight pulling downwards is also 80,000 newtons. When we subtract one from the other, we get 0 newtons in the vertical direction, which means these forces are balanced, and there is no net vertical movement. For the horizontal component of the forces, let us say the thrust moving the plane forward is 120,000 newtons, while the air resistance pulling it backward is 90,000 newtons. If we subtract the smaller backward force from the larger forward force, we are left with the resultant force of 30,000 newtons acting in the forward direction. So when we combine both vertical and horizontal analyses, we find that the plane has no net vertical force and a net horizontal force of 30,000 newtons, pushing it to the right or forward. However, if the scenario were slightly different and the air resistance increased to also be 120,000 newtons, then both the thrust and the drag would be equal. In that case, 120,000 minus 120,000 equals 0, and so the resultant horizontal force would also be 0. With both vertical and horizontal components now perfectly balanced, we would say the object is in a state of equilibrium. This means that there is no net or resultant force acting on it, and therefore it would not accelerate but would instead remain in a steady state of motion or rest, depending on its initial condition. That wraps up everything we wanted to go over in this video. We hope you found this explanation helpful and that you now feel more confident using free body diagrams to analyze forces. Thanks for watching, and we'll see you again in the next video.